Let's talk about mass spectrometry now. We've covered infrared spectroscopy, and now we're going to talk about mass spectrometry. Spectroscopy was the interaction between matter and light, and mass spectrometry deals with the interaction between matter and energy, namely that we're going to be subjecting a organic compound to a high energy beam of electrons. And what's the main driving force behind why we do mass spectrometry is that it's usually used to determine the molar mass and the molecular formula of a compound. That's usually what we try to do. You know, you want to find out how many carbons, how many hydrogens, how many oxygens there are in some kind of compound. Well, in that case, we often use mass spec. So what happens in a mass spectrometer? First thing that happens is the compound is vaporized, then ionized, and then it undergoes fragmentation. And then the masses of those ions are detected and graphed. A couple of important points here. The first one is that the compound is vaporized. And you might be thinking, well, Mr. Dion, what if the compound is a solid that has a really high melting point? How would you vaporize it? Well, what we do is we heat up the compound at a very high temperature and we put it under a vacuum. So that reduces its vapor pressure and allows it to be converted into a gas. And then ionization occurs when the molecule is hit with a high energy beam of electrons. And when it's hit with those electrons, it's going to knock an electron from the molecule, which causes it to fall apart. And we call that breaking apart or falling apart. We call that fragmentation. And then the ions of those fragments are graphed according to their masses. And so it's important to note that the only masses that we see in the mass spectrum come from ions. Okay, it's got to be ions. The only masses we see come from ions. You do not see any uncharged fragments in a mass spectrum. Now, there are different types of mass spectrometry, and there's a part of chapter 14 that we skip, and it deals with high resolution mass spectrometry. And so all the mass spectrometry that we are doing in this class is low resolution mass spectrometry. I'll just call it low resolution MS. And the masses that we're going to use for the elements in low resolution mass spectrometry will just be given to the ones place. And so hydrogen will have a mass of 1 atomic mass unit, not 1.01. Carbon will have a mass of 12. Nitrogen will have a mass of 14. Oxygen will have a mass of 16. Chlorine will have a mass of 35. Bromine will have a mass of 79. And sulfur, which we might see from time to time, will have a mass of 32. So those are the elements that we're going to encounter most commonly. And those are the masses that we're going to use for those atoms. So let's say we had, methane, and we were trying to calculate the molar mass of methane. We would say 12 plus 1 times 4, and that would give you 16 atomic mass units. Okay, would be the mass of methane, etc., etc. All right, well, let's move on from there. And how do we ionize these molecules? Well, the most common method of ionizing molecules is using something called EI, which stands for electron impact. What happens is we bombard the sample with a high energy beam of electrons. Very high energy. We just hit it with this big old beam of electrons, which has an energy of around 1600 kilocalories, and it usually causes an electron to be ejected from a molecule. So if you have an uncharged molecule and you hit it with the beam of electrons and it loses an electron, well, if something loses an electron, what are you left over with? You're left over with a cation. Well, if the molecule has lost an electron, that means it's got an unpaired electron. What do we call an unpaired electron? We call an unpaired electron a radical. And so we put them together and we say we have a radical cation. We have something that has an unpaired electron and a positive charge. The mass of the radical cation is the same as the parent compound. So again, the radical cation has the same mass as the parent. Why would that be? Because an electron has such a small mass that when you lose one electron, it has such a small effect on the mass that we can basically negate it. If you go back to your general chemistry 1 days, an electron is roughly, 2,000 times lighter than a proton. So it doesn't affect the mass all that much. So same mass as parent. Okay, so now we've got a radical cation, and we can detect the mass of that cation, and we know that it has the same molecular mass as the parent. This is our parent. And so if the radical cation remains intact, we call that the molecular ion. That radical cation that we see that just lost one electron from the parent, we call that the molecular ion, and we call that M+, and we put that little dot up in the corner, so we write M+ for the parent, which is a cation, but then we put the little dot there, which represents that it's a radical. So we call that the parent ion or the molecular ion. I'm usually going to call it the molecular ion, but again, the molecular ion would have the mass of the parent. So if we look at the molecular ion, we know the mass of the compound that was put into the mass spectrometer. Now, if you take a look at this thing here, this radical cation, so this radical cation here, you're probably thinking, Mr. Vian, that doesn't look very stable to me. I mean, what the heck is this? You just took a molecule and you knocked an electron out of it. That doesn't sound like something that's going to stick around forever. I think you're right. That doesn't sound very stable to me either. And it says here that most of the radical cations, the parent ions, the molecular ions, are going to fragment to give you a radical and a cation. So the radical cation will break apart. Don't worry about the curved arrow here. Don't worry about it right now. But when you have a fishhook arrow like this, it represents the flow of one electron. So the radical goes to one side. So we make a radical, and then you're left over with a carbocation. Well, remember, the only thing that you're going to see in a mass spec is something with a charge. So detected, you're going to see the carbocation. It will be detected in the mass spectrum, the MS. So mass spectrometry, we just use MS. Whereas the radical is not going to be detected, not detected since it has no charge. We only detect things that have a charge. So what happens is that parent, that radical cation that's formed, it's going to get deflected by a magnetic field. Then all the different ions that are produced from a molecule will be plotted according to their mass to charge ratio. Again, we don't see any neutrally charged fragments. Now, one other thing I want to get right out of the way at the very beginning of mass spectrometry is when we're talking about mass over charge, so we call that M over Z, mass over charge. The only Z you're ever going to see in this class, Z will always be, ready for this, +1. So if you take the mass and you divide it by +1, what does it equal? The mass. So any masses that you see in a mass spectrum in this class will be the mass of the fragment. Okay. Now what's so cool about mass spec is that if you have a complicated organic molecule, it's always going to fragment in a predictable way. And if you have a simple organic molecule, it's going to fragment in a predictable way. If you have the simplest possible organic molecule, which is this here, methane, it's going to fragment in a predictable way. So let's take a look at the mass spectrum of methane, and let's go over a couple more definitions. The mass spectrum, that's this right here. Here's our mass spectrum. We see the fragments plotted by their mass to charge ratio, and then we see the relative abundance. Which one is the most abundant of all of these peaks? Well, this is the most abundant peak here. And whatever the tallest peak is in your mass spectrum, the tallest peak, we call that the base peak. Therefore, this would be our base peak. Now, the base peak is sometimes the molecular ion, but it's not always the molecular ion. It's not always the parent ion. Now, in methane, it just happens to be. Because if we calculate the mass of methane, methane is carbon has a mass of 12, and hydrogen has a mass of 1. There's only one carbon, and there's 4 hydrogens. So that gives us 12 plus 4. That gives us 16. Well, if we zoom in on our mass spectrum, you see that we have 15, and our base peak just happens to be the molecular ion. The molecular ion has a mass over charge equal to 16. But we see that we have some other peaks in there as well. Now, again, in methane, the base peak happens to be the parent ion, right? Our base peak, the tallest peak, happens to be the molecular ion, but that's not always the case. Now, your eye is probably drawn to, well, what the heck is this, Mr. Dion? There's something here with a mass over charge that's equal to 15. There's something here with a mass over charge that's equal to 14. It's not very big. Then you have 13. Then you have 12. And look, there's even something that's heavier. There's something really small. It's not very big, but there's something with a mass over charge of 17. Where the heck did that come from? What did you do? Create matter? How did you end up with something that's more heavy? Well, we have an explanation for that. Let's take a look at some of those fragments, some of those ions that have masses less than 16. Check it out. If you have that molecular ion that's formed when you bombard methane with a high energy beam of electrons, well, what if you lose a hydrogen radical? Then you're left over with a methyl carbocation that has a mass of 15. And so we go back here and we see that mass over charge of 15. That represents the methyl carbocation. But what about the mass over charge of 14, Mr. Dion? Where did that come from? Or 13 or 12? Well, what happens is the radical is going to keep losing hydrogens to give us these different masses of 12, 13, and 14. Now, if you're wondering, can you show me, what does that look like when it breaks apart and breaks apart again and again and again and again? Don't worry about that quite yet. Let's just worry about the most important points of mass spec since we're just learning the subject. I told you before I started recording this that if you are interested in mass spec and you are good at mass spectrometry, if you have a talent for it or a knack for it, or maybe even just a love for it, there's lots of employment opportunities for people who are interested in mass spectrometry. Where would you use mass spec? Well, in the pharmaceutical industry, when humans or animals are dosed drugs that are experimental, they have to monitor the drug metabolism. And so in order to detect metabolites in blood and serum and plasma, they oftentimes use mass spec. In biotech, determining the sequence of amino acids and proteins and peptides and enzymes, we use mass spec to do that. What else? Some other cool ones. Another big one is forensics. Not only explosive detection, but just detection of metabolites in tissues and blood and serum after somebody has died. I mean, I'm sure that everybody here has seen, or a lot of people have seen these crime shows where they're analyzing blood and looking for traces of maybe illegal drugs and things like that. And again, there's a lot of opportunity for mass spec. Another big one that's important at UCCS is that UCCS does some mass spectrometry testing of water samples and also looking at flavor profiles of whiskeys and things like that. I'm not an expert in that. But anyhow, there we go. So that's the introduction to mass spec. Well, let's dig in a little bit deeper. Let's get some more information here. Let's take a look at the mass spec for benzene. What's the mass of benzene? You might need a calculator if you're not as fast at your mental math as you want to be. So let's see. Benzene has a formula of C6H6. So that's 12 times 6, which gives us 72. So that's 72 plus 6 gives us 78. If you lose one electron from benzene, you should have a parent ion at 78. We zoom in here, we see 80. This would be 79. And what do you know? We have something with a mass over charge that's equal to 78. And this also happens to be the parent ion or the molecular ion. It's also happening to be the base peak because the base peak was what? The tallest peak. So it's the molecular ion and it's the base peak. The base peak. It's both. Now, why is the base peak so dang big for benzene? Something that we haven't covered yet, and we'll talk about more as the class goes on, is benzene is a very stable molecule. So we'll put here very stable molecule. And the reason we don't see a lot of fragments, I mean, there's a few here and a few here. The reason we don't see a ton of fragments with benzene is because it doesn't fragment easily. It's a really, really stable compound. And before I move on, let me just address another thing. It's that what are we doing right now? We are just being introduced to mass spec and we're trying to learn mass spec. We're learning the concepts. So if you read the textbook, he points out, you know, do not worry about every single peak. What is this peak? What is this peak? What is this one? And this one? And this one? And this one? And this one? What is every single peak in here? Well, the good news is this. You don't have to worry about every single peak in the mass spectrum. That would be not impossible, but it would be way beyond the scope of our course. What you have to train your eye to be able to do is look for the low-hanging fruit, the most important points, or the most important peaks in the mass spectrum. What are we doing right now? We're learning how to identify the most important peaks in the mass spectrum. Well, it says here that unlike benzene, in most compounds, the molecular ion is actually not the base peak. Check this out. If you have butane, well, what's the mass of butane? Let's see here. It's C5H12. So that's 60 plus 12, which gives you 72. Do we have an ion at 72? Let's take a look. This is 70, 71, 72, 73, 74, 75. So it turns out we do have our molecular ion here. That is our parent. It has a mass over charge that's equal to 72. However, it's not the base peak in this compound, is it? No, not at all. The base peak is right here. Here is our base peak. That's our base peak because the base peak is the tallest peak in the spectrum. Well, what the heck is the mass of the base peak? Let's look. It's this one. It's this one here. So we go 40, 41, 42, 43. So 43. Our base peak has a mass over charge of 43. Now remember, everything that you see in here is some kind of ion. Well, what would the compound have to lose in order to end up with a fragment that has a mass of 43? Let's do it. 72 minus 43 gives you 29. So not only can we call this base peak and say it has, or not only can we say it has a mass over charge of 43, but you could also call this the parent. Okay, we could call this the parent minus 29. Right? The difference between 72 and 43 is 29. Well, what the heck weighs 29? Let's wait and we'll see what has a mass of 29 and we'll come back to it. All right. So going back to that molecular ion, let's talk about it a little bit more. You notice that here in the title, it puts the M in brackets and then it has the positive charge and the radical outside of it. And here it doesn't. It just depends on the book. You know, it depends on the publisher sometimes. I like to just write it like this. That's my way of doing it. Anyhow, let's go back here. Okay. The mass over charge of the parent is the molar mass of the compound. Remember, the mass over charge of the parent is the molecular ion. Okay. Well, there's a really neat rule that we call the nitrogen rule that helps us get some information from a molecular ion or a parent ion. It's this. If you have an odd massed molecular ion, it means that there's going to be an odd number of nitrogens in a molecule. Okay, simple as that. You have an odd mass, you have an odd number of nitrogens. Check this out. If we go back, butane had an even mass, it didn't have any nitrogens. You go back to benzene, it had an even mass, it didn't have any nitrogens. But check this out. If you look at this compound here, it's got one nitrogen in it and it's got an odd mass. Take a look. This compound has no nitrogens. It's got an even mass. Well, you might be looking at this compound down here and say, well, that's got an even mass and it's got nitrogen, but hold on, there's more. If you have an even massed molecular ion, it generally indicates one of two things. Either there's no nitrogen, okay, none, or an even number of nitrogens. So since we have an even number of nitrogens, we end up with an even mass. And this is called the nitrogen rule, is what I call this. So let's call this whole thing here the nitrogen rule. And this is a rule you've got to know. It comes up over and over and over in organic chemistry. Every time we look at a mass spectrum, we always talk about the nitrogen rule. Well, let's go back to that mass spec of methane. And we saw that the base peak of methane was this peak right here, which has a mass over charge equal to 16. Therefore, it is also the molecular ion. Well, you might have noticed, and I pointed it out quickly, that there was something with a mass over charge of 17. Now, instead of just saying it's got a mass over charge of 17, the way we describe that is we call it an M+1 parent. Okay, we call it M+1 molecular ion. So I'm going to label it here. This is the M+1 molecular ion. Well, where did you get the parent +1? Where did the +1 come from? Well, it comes from carbon-13. Remember carbon-13 when you talked about isotopes of carbon? Well, there's 3 isotopes of carbon. There's carbon-12, so carbon-12. Then there's carbon-13, and there's carbon-14. Carbon-12 is something like 98.9% of all carbons are carbon-12. And then carbon-13 is about 1%, and the rest, we'll just put here, the rest is a carbon-14. So very little carbon-14 in hydrocarbons, but about 1% of carbons are carbon-13. Well, if you measure the height of this peak, and we're not going to do it right now, but if you take the base peak as being 100%, because it's the tallest peak in the spectrum, the height of this peak is about 1% of that, right? Because 1 out of about 100 carbons is a carbon-13. Now, carbon-13 has a mass of 13. Therefore, the mass here is 13 plus 4, which gives us 17 for our molecular ion. Pretty cool, huh? Now, you might be wondering, well, okay, Mr. Dion, that's when you have one carbon atom. But if you have more than one carbon atom, every single carbon atom has a 1% probability of being a carbon-13. Let's address that. What if you had a compound like decane? What's decane? Decane is C10H20, not H12, H22. Okay. Well, if we take a look at the M+1 peak for decane, see that decane has a parent, which happens to be the base peak, and it has a mass over charge of 142. But then you see you have something here that's 143. Well, remember, decane has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons in it. So that means there's a 10% chance that in every one out of every 100 carbons is a chance of being a carbon-13, but there's 10 carbons. That means the M+1 peak is going to be 1% times 10. And so if this molecular ion has an abundance of 100%, then this should be about 10%. So it's about 10% the height. And so by comparing the heights of the molecular ion and the M+1 peak, you can estimate how many carbons are in the molecule. Now, I'm not going to go over any problems about that today. However, there's a really fantastic skill builder where they get you to apply this rationale. You look at a hydrocarbon and you say, well, there's this many hydrogens in it, this many carbons the abundance of the M+1 peak is this much, and therefore I can predict how many carbons are in the molecule. So pretty neat thing that you can do there. And again, I'm not going to go over the skill builder today, but I highly recommend that you take a look at this. It won't take long. It's not the longest skill builder in the world. Well, that covers the M+1 peak. Well, are you ready to have your mind blown some more? Right, it's fun learning new things in organic chemistry, and here's some more utility we can get from a mass spec. Now, if you were with me this morning before I started recording today's lecture, there's 2 halogens that I brought up. I brought up chlorine and bromine. And when we get into chapter 7 in this class, we're going to be talking about chlorine and bromine all the time and how they're involved in reactions called substitution reactions and elimination reactions. But before we get into that, let's talk about the utility of chlorine and bromine and what can be gained or garnered from having those atoms in an organic compound when we run its mass spectrum. So chlorine has two abundant isotopes. Now, these are things that you've got to have kind of in your hat once you step into the quiz. Chlorine can be either chlorine 35 or chlorine 37. The relative abundances are 76 and 24%. You could say that they have an approximate ratio of 3 to 1. So if you have a molecule of chlorobenzene, let's say, well, it means that if you have, 4 molecules of chlorobenzene, one of them is going to be having a chlorine with a mass of 37, but the other 3 will have a mass of 35. Put another way, if you look at the mass spec of chlorobenzene, you're going to have an M+2 molecular ion. What would be the height of the M+2 molecular ion? Well, if the if the M plus has a height of 3, okay, if this is your M plus, then your M+2, so your M+2 molecular ion should have a height that's about 1/3. Now, did I make that about a third? It's close to it, but it should be about 1/3 the height. Check this out. If we look at chlorobenzene, it has a formula of C6H5Cl. So let's tally that up. So we've got 6 times 12, which gives us 72, plus 5, plus we use the most abundant isotope of chlorine, which is 35. So we take 72 plus 40, and we end up with 112. Let's zoom in. So if this is 100, this is 105, this is 110, this would be 115. So 111, 112. So our base peak is our molecular ion, and it has a mass over charge of 112. 113 is really small, but you see that you have something that has a mass over charge that is equal to 114, and that would be our M+2 molecular ion. Well, you notice that if the height of this is about, if we assign that a value of 3, this is about 1. So we have a 3 to 1 height ratio for our parent and our M+2. That means that we have chlorine in our molecule. That's how we can recognize chlorine as being in our molecule, just by looking at the molecular ion and the M+2 molecular ion. Well, I brought up bromine. How would you do something similar with bromine? Bromine has 2 abundant isotopes. You need to know them. However, they appear in a different relative abundance. Bromine 79 has an abundance of 51%, and bromine 81 is about 49%. Therefore, the ratio of the M plus to the M+1 is going to be about 1 to 1. We take a look at the formula of bromobenzene. We have C6H5Br. So we take C6, which is 72 plus 5 plus 79. So that's 72 plus 84. That gives us 156. Here is our molecular ion, which has a mass over charge equal to 156. However, you look and see that we have an M+2 ion, which has a height that's almost equal to that of the molecular ion. Well, that has a mass over charge of 158. And since they have a 1-to-1 ratio, it tells us that we have bromine in the molecule. And therefore, the conclusion is this. If you have an M+2 peak that is 1/3 the height of the molecular ion, you've got chlorine in your molecule. And if you have an M+2 peak that has a relative height that's almost the same as the molecular ion, the parent, then you have bromine in your molecule. Pretty cool, huh? So not only have we learned that just by looking at whether the mass of the compound is odd or even, we can determine whether or not we have nitrogen in the molecule. And now we've looked at the molecular ion, and we can determine whether we have a halogen, chlorine, or bromine in the molecule.